lecture we discuss about different type of singularity. Today we discuss some more concept related to the singularity, then we solve some numerical problem, then we discuss about residue, how we define the residue and how we find the residue. Then if time permit, then we discuss about Cauchy residue theorem. So what is the value of if we talk about singularity at infinite, at z equal infinite. So how we categorize the singularity at z equal infinite? So suppose means singularity at z equal infinite means we talk about extended complex plane, means complex plane with point infinite become what? Extended complex plane. So suppose there exists a region, means R in a such a manner, this one is a R, there exists a region mod z minus z0 is greater than R, So here this one is a z0, or if we talk about a what? Here what we talk about are not z minus z0, suppose we assume that center at 0, 0, then what will happen? This one is at 0, 0, z0 equals 0, 0. Then mod of z is greater than R. For this reason, means this one is a C which enclosed all the singular points, and mod of z greater than R, there is no any other singular point except z equal infinite. Means in this region, in our outer region, in this region, there is no any singular point if we write in terms of word sentences, then means in this region, in mod of z is greater than R, there is no singular point, except z equal infinite. So what will happen? Here we are able to find out what? A deleted neighborhood like this one, we replace z equal what? Z equal 1 upon w. Then this become mod of 1 upon w, mod of 1 upon w is less than 1 upon r and greater than what? Greater than c. This one is a deleted neighborhood. Inside this neighborhood, there is one singular point. One singular point means z equal 0. W equal 0, not z equal 0. W equal to 0. If we transform from z plane to w plane. So here, the behavior of a z at infinite, the behavior at z equal infinite is equivalent to the behavior at w equal 0. So either we identify the singularity at w equal to 0 in this region, or we identify the singularity at z equal infinite. So what will happen here, if we talk about w equal to 0, behavior of w equal to 0. So what will happen in this region? 1 upon w less than 1 upon r greater than 0. In this region, only at z equals 0 function is not analytic. So if at w equal if at w equal, if we write not here, if we write here, if at w equal what? If we write here, if at w equal 0, have isolated singular points, w equals 0 have isolated singular point, isolated singular point, then z equal infinite have also isolated singular point, Similarly, if w equals 0, have a removable singular point, removable singularity, or pole, or essential singularity, then same happen at z equal infinite. Z equal infinite have also what? A removable singular point. Singular point or pole or essential singular point. Essential singular points. So rather than to examine the singularity at z equal infinite, there is a need to examine the singularity at w equal 0. So if fz is a what? Fz is a given function. Then we replace fz by, here we write f of 1 upon w. Suppose here we write f1 upon w, 1 upon w or fw. Then to examine the nature of a singularity at z equal infinite, we examine the nature of a singularity at w equal 0. So both have a same meaning. So either we examine the behavior of singularity at z equal infinite, or singularity at z equal infinite, or w equal 0. Both have a same nature. So this one is all about singularity at z equal infinite. Now we solve some numerical example based on a previous lecture and this lecture. We try to classify the singularity. So once we raise out this one, then we examine the singularity. First, examine the singularity. The nature of singularity. First question is the example. These are the examples. First question is what? E to power z upon z minus sin z at z equals 0. Second one, e to power z upon z plus sin z at z equals 0. And third one, twice at z equal infinite. So what is the question? Question is examine the nature of a singularity at z equals 0 of this function e to power z upon z minus sin z, e to power z upon z plus sin z at z equals 0. And here we examine the singularity at z equal infinite of z to power 4 plus 2z square plus 1z square plus 5z plus 2. So one by one we examine the singularity. So here we examine the singularity. What are the types of a singularity at z equals 0? First one, if we try to solve, first one, fz equal what? Fz equal e to power z upon z minus sin z. Sin z. So either this one is a isolated singular point or non-isolated singular point. So this can be classified, means if there exists so z equals 0, and z equal sin z equal z, and there are several singular points. So this one is at z equals 0, there is a what? Isolated singular point. Isolated singular point. Isolated singular point. Isolated singular point. Because we are able to find out a small neighborhood where there is only one point which is a singular point. Because there is a means 0 to pi, there is a means gap between 0 to pi, then we draw a small neighborhood between 0 to pi which includes only the c. So now this one have a pole or essential singularity or removable singularity. So this can be decided limit z 0 fz. What is the value for this one? Limit z tends to 0. Limit z tends to 0 e to power z upon z minus sin z. Sin z, this one equal to what? Infinite. What is the meaning of this one? This one indicates that there is a pole. At z equals 0, there is a pole. Poles. But what is the order of a pole? This can be decided on the basis of this one. Suppose here we write fz as a pz upon qz. Now what is the value of a pz? And this one equal what? P to power z upon z minus sin z. So first we write qz as a what? Qz equal z minus sin z. Here we write z minus sin z is a what? Why here we write? Because q0 is a what? Q0 is a 0. What is our aim? Our aim is to write this one in this form. pz0 upon z minus z0 to power m gz, provided what? gz0 does not equal to 0. gz0 does not equal to 0. Now we try to write in this form, z minus z0 to power m gz, and pz0 does not equal to 0 here. This one is a, and pz is a what? Pz is a e to power z, and p0 is a what? P0 is a e to power 0, and this one is not equal to 0. So this one is a basic condition, means numerator at z equals 0 does not equal to 0. So pz0 does not equal to 0. Now we try to write a denominator qz in a form of a z minus z0 to power m gz, provided gz0 does not equal to 0. So here, since qz is a 0, so what we write here? Here we write the expansion of a sin z. Sin z is a what? Z minus z cube upon factorial 3 plus z to power 5 upon factorial 5 up to infinite number of terms. So if we simplify this one, z and z, this one cancel out, then this become z cube upon factorial 3 minus z to power 5 upon factorial 5 and so on up to infinite number of terms. So what will happen if we take z square common, not a z square, this one is a z cube common here, then z cube common, then this become what? This become 1 upon factorial 3 minus z square upon factorial 5. Z square minus factorial 5, this one is a z minus sin z. So z minus sin z, so z minus sin z, z minus z cube upon factorial 3, z to power upon factorial 5 up to infinite. So z and z cancel out, so this becomes z cube and so on up to infinite number of terms. So now we are able to write qz equal what? Gz, not a gz, here we write z minus 0 whole cube and gz, and gz is what? Gz become what? Gz become 1 upon factorial 3 minus z square upon factorial 5, and how many number of terms? Infinite number of terms. At z equals 0, because we examine the singularity at z equals 0. So at z equals 0, what is the value? G0 does not equal to 0. So now we are able to write this one in this form. So here, if we try to write here, what is the fz? Fz equal what? Fz, now here we write fz. If we write this one in this form here, this one in this form here, fz equal e to power z divided by z cube minus 0, z minus 0 whole cube, and here gz. This one is a gz, this one is a gz, this one is a gz. So here gz0 does not equal to 0, g0 does not equal to 0. So what is the behavior? What is the value of m? If we compare here, what is the value for m? M become what? M equal 3. So this one have a pole of order 3. How we decide? Z equals 0, at z tends to 0, this one is infinite, then this one is a pole of order. Pole at z equals 0, what is the order of a pole? We write pz upon qz. Then at z equals 0, pz0 does not equal to 0, and we write qz in form of a z minus z0 to power m. Gz, provided gz0 does not equal to 0, if we write in this form, then what is the power of a z? Power of a z is a 3. So what is the behavior of a singularity? So at z equal, what we decide? At z equals 0, there is a pole of order 3. Pole of order 3. So this one is your first question. Now if we solve the second one, then how we solve? In a similar manner, we also try to solve the second one and try to examine what is the behavior at z equal 0. So now at z equals 0, here, second one. Fz is a what? Fz equal e to power z divided by z plus sin z. So here, this one, suppose this one equal what? Pz upon qz, Pz upon qz. Now what will happen here? This become, now Pz0 means P0, Z0 is what? Z equals 0. P0 now does not equal to 0 because e to power 0 become 1. Now Q0 equal what? 0. Now we write the Qz in the form of a what? Z minus Z0 to power m Zz, provided Cz0 does not equal to 0. We try to write in this form. If this one is a what? This one is a pole. This one have a pole. So here already we checked this one is a limit. Now limit z tends to 0 of a fz is a what? Infinite. So this indicates that there is a pole. Now what is the order of a pole? This can be decided if we write gz in this form. Qz in this form. So qz here we write this one qz like this one. Qz equal z plus sin z. We expand the sin z, then z plus Sin z is a what? Z minus z cube upon factorial 3 plus z to power 5 upon factorial 5 up to infinite number of terms. So if we simplify this one, qz become what? Qz become twice z minus z cube upon factorial 3 plus z to power 5 upon factorial 5 and so on. So if we closely observe, z may be taken outside from this one. So what is the qz? Now qz become z into what? Twice minus, this one is it, 2 minus z square upon factorial 3 plus z to power 4 upon factorial 5 and so on up to infinite number of a term. So if we closely observe this one is a what? Z minus 0 and this one becomes zz. At z equal to 0, this one does not equal to 0. So what will happen here? Z0 does not equal to 0 because what is the value of G0? G0 become 2. So G0 does not equal to 0. So we able to write in this form. Qz in this form. So if we write Fz like this one, you may write Fz equal what? E to power z divided by z minus 0 into Gz. Gz are you right? This one is a Gz. And what? Z0 does not equal to 0 and P0 also does not equal to 0. P0, this one is a Pz. So if we compare with the standard result, what is the standard result? Fz equal Pz upon z minus z0 to power m Zz provided Pz0 does not equal to 0, Zz0 does not equal to 0. Then what is the order of a pole? Order of a pole is a m. So if we compare here, what is the value of m? M is a 1. M equal 1. So what we conclude, Fz have simple pole. Simple pole. So this one is a solution of a second one. Now we try to solve third question. Means behavior of a singularity at z equal infinite. So at z equal infinite. So what is the behavior at z equal infinite? So if we solve the third one, then what is the value? Here if we erase out this one, then here we write third one, Fz equal z to power 4 plus twice z square plus 1 divided by z square plus 5z plus twice at z equal infinite. So we know that as earlier we discussed that the behavior at z equal infinite is equivalent to the behavior at z equal or w equal 0 if we replace z equal 1 by w. So here we write f of w equal f of 1 upon w. So this becomes 1 upon w to power 4 plus twice 1 upon w square plus 1 divided by 1 by w whole square plus 5 times 1 by w plus twice. Then here we examine the behavior at w equal 0. Both have a same meaning. Earlier we discussed about this one. So now if we simplify this one, now fw become what? Fw become w to power 4 plus twice w square plus 1 divided by w to power 4, and here this become twice w square plus 5w 5w plus 1 and into what? W for 4 from here, w square from here. So this become 1 upon w square. 1 upon w square. So what is the behavior at w equal to 0? So if we closely observe here, w equals 0 is a one singular point and there is some other singular point by putting w 2w square plus 5w plus 1 equal 0. So what are the singular points? W equals 0 be a one singular point and another one is a w equal minus b means a minus 5 plus minus under root b square 25 minus 4 into 2 divided by what? Divided by 2 4. So there means a finite number of points. So w equal to 0, what here we categorize w equal 0 is a isolated singular point because there is a finite number of singular points. So we able to draw at w equal to 0 there is a small circle. Inside this circle there is no any other points. So w equal to 0, w equal to 0. So we categorize as a w equal to 0 is a what? W equal to 0 is a isolated singular point. Isolated singular point. Isolated singular point. Now, under the isolated singular points, this one is a removable singular points or pole or means a pole of order m or essential singular points. So if we closely observe this expression, this one is a in this form fw equal, this one is a pw divided by w minus 0 whole square and here zw. What is the zw? This one is a zw. We compare this one is a what? This one is a zw. This one is a zw. This one is a what? This one is a pw. This one is a pw. What is the value for p0? p0 does not equal to 0 because what is the value of p0? p0 is a 1. p0 is the 1. If we write not in this form, we write p0 like this one. p0 equal what? p0 equal 1 and this one does not equal to 0. Similarly, what is the value of z0? z0, this one is also a 1, this one also does not equal to 0. So this one is in the form of a what? fw in the form of a pw upon w minus 0 whole square cw. So what is the similarity at w equal to 0? So here if we compare w minus 0 to power m, so here what is the value for m? M is a 2. So there exists a pole of order 2 at w equal 0. At w equal 0. So as previously discussed, the behavior at z equal infinite is equivalent to the behavior at w equal 0. So what we conclude? We conclude that w equal to 0 have isolated singular point and w equal 0 if we categorize under the isolated singular point, this one is a pole of order 2. So what we conclude? We conclude that w equal to 0 have a isolated singular point, isolated singularity, isolated singular point, and this one is a pole of order 2. So this one is equivalent to what? This one is equivalent to for z equal infinite. What is the meaning of this one? Means at z equal infinite, function have a isolated singular point of and that isolated singular point is a pole of order 2. So this one is all about a singularity, means some numerical example based on a singular point, how we classify the singularity. So only on the basis of a denominator, you cannot say directly this one is a isolated or non-isolated. So you may write, first you decide this one is isolated or non-isolated. If you able to decide isolated or non-isolated, then under the category of isolated, if we able to write in this form, means limit z tends to z0 fz equal infinite, then there exists a pole, and if there exists a pole, then what will happen? You'll be able to write Pz upon Z minus Z0 to power of m Gz, provided Gz0 and Pz0 does not equal to 0, then the pole of order m. And in case of a essential singularity, limit Z tends to Z0, Fz, if the limit does not exist, either finite or infinite, then we say that there exists essential singularity. And in case of essential singularity, only way to decide with the help of a Lorentz expansion having a infinite number of terms.